The throughput of a modern AI data center is strictly capped by the rate at which data travels between memory and the processor. In these environments, memory bandwidth has overtaken raw compute power as the primary hardware constraint. Storing information as electrical charge creates a structural bottleneck known as the memory wall. This is a limit imposed by the physics of electrons, rather than a lack of engineering refinement. Charge-based storage is defined by energy loss. Capacitors leak, requiring mandatory refresh cycles that consume power even when the data isn't being accessed. As cells shrink, these leakage currents and capacitive scaling limits become impossible to manage without massive energy overhead. Compare a silicon floating gate on the left to a carbon-fluorine bond on the right. The gate stores electrons, requiring continuous electrical pulses to prevent leakage. The lattice stores data as geometric position. Anchored by covalent forces, it remains perfectly static with zero energy input. This physical limitation is meeting a market crisis. NAND flash supply is struggling to keep pace with the massive data ingestion required by large language models, driving contract prices up by nearly 40% in a single year. Reaching atomic scale density requires moving past the storage of electrons. The binary state must be encoded within the geometric orientation of the covalent bonds themselves. Single-layer fluorographene provides this geometry. It is a two-dimensional material that allows for non-volatile storage at the scale of individual atoms. The thermodynamic limits of moving electrons mean that further memory scaling is now a problem for material science rather than electronic engineering. Fluorographene is a fully fluorinated derivative of graphene. Every carbon atom in the sheet adopts an sp3 hybridized state, meaning it is covalently bonded to exactly one fluorine atom. This model shows the resulting structure. The teal fluorine atoms are distributed across a carbon scaffold. Its natural three-dimensional corrugation and bilateral symmetry, the alternating atoms above and below the plane, cancels out internal strain that would otherwise force the sheet to curl. This yields a binary degree of freedom. A fluorine atom pointing up relative to the carbon plane represents a 1. Pointing down represents a 0. These orientations are locked by covalent bonds, making them resistant to radiation. To prove the stability of this bit, we have to look at the physics of the irreducible memory unit. This molecular model, fluorophenylene, calculates the energy required to flip a single bit. The F up state on the left and F down state on the right are stable equilibrium geometries. The bit is located precisely at this bridgehead carbon. In a freestanding sheet, these two states are energetically identical. The slight corrugation of the lattice introduces an energy difference of less than 10 millielectron volts. Because this energy split is significantly lower than the ambient thermal energy at room temperature, there is no thermodynamic force pushing the bit to prefer one state over the other. This equivalency means the bit does not suffer from the gradual voltage decay found in capacitive memory. It is a discrete geometric state that does not drift. The central problem is moving the atom between these two stable positions without breaking the covalent bond that anchors it. This graph represents the energy landscape of the bit. To flip, the fluorine crosses a transition state barrier of 4.6 electron volts. For comparison, breaking the carbon-fluorine bond requires 5.6 electron volts. This 1 electron volt gap ensures the atom flips without the bond rupturing. The atom crosses this landscape through a process called pyramidal inversion. During inversion, the central carbon flattens. The fluorine atom physically squeezes through the narrow gap between 3 surrounding carbons, snapping into the opposite orientation. This 4.6 electron volt barrier is exceptionally high for a single atom. It results in a thermal bit flip rate of 10 to the negative 65th events per second, a retention time trillions of times longer than the age of the universe. But at the atomic scale, we must also prevent quantum tunneling, where an atom simply disappears from one side of a barrier and reappears on the other. Tunneling is governed by the WKB approximation. The lighter the atom, the more likely it tunnels. Hydrogen would erase data every few weeks. Fluorine, 19 times heavier, mathematically suppresses tunneling to 10 to the negative 76th events per second. Heavier elements like chlorine or bromine don't work because their physical size is too large to pass through the carbon base ring during inversion. Fluorine is the only element that combines the necessary mass to stop tunneling with a size that allows for inversion without bond rupture. Stability is only useful if the data can be addressed, read, and rewritten at high speeds. Because the carbon and fluorine are covalently linked, when the fluorine atom inverts, it pulls the central carbon atom with it. This creates a physical topography. A scanning probe on face A detects a mound where the fluorine atom protrudes. Simultaneously, a probe on the opposite face scans the same site, detecting a trough where the carbon atom has dipped away. This dual-face topography allows the hardware to verify every bit automatically. A valid site must report a mound on one side and a trough on the other. Any other signal is a defect. For writing, a Tier 1 probe applies a 3 to 5 volt pulse. This generates an electric field that couples to the carbon-fluorine dipole, lowering the energy barrier enough to drive the inversion. Tier 2 high-speed writing uses a method called resonant vibrational ladder climbing. A MEMS-actuated array delivers a 37 terahertz mid-infrared pulse, tuned to the exact stretching resonance of the carbon-fluorine bond. Absorbing energy over multiple cycles, it builds localized kinetic energy to push the atom over the 4.6 electron-volt barrier. Because reading is a topographic measurement and writing uses vibrational resonance, this system avoids the oxide wear and voltage shifts that limit the lifespan of flash memory. In this lattice, each bit site is separated by 0.254 nanometers. This means every square nanometer contains 35 bits. When we scale that atomic density to a square centimeter, the sheet holds 3.5 quadrillion bits, or 447 terabytes. We can scale this further by framing the material into continuous nanotape spools. At this density, a cubic centimeter of tape can store up to 9 zettabytes. Fabricating this does not require the 700 cleanroom steps or the multi-billion-dollar lithography machines used in the silicon industry. The material is synthesized by passing a sheet of graphene through a vapor of xenon difluoride. The carbons convert to the sp3 state automatically as they accept the fluorine atoms. This process changes the economics of memory production because the chemical exposure sets the bitmap during the material synthesis. There is no initialization phase. The raw material exits the chamber already carrying a random, readable bitmap. The material itself is the memory device. For data centers, this means storage with zero retention power and total resistance to ionizing radiation. Cooling requirements are reduced to passive airflow. Closing the gap between AI processing power and memory bandwidth will require moving beyond lithography and returning to covalent chemistry, building an infrastructure that is limited only by the physical constraints of the universe.